Imagine an examiner gives you a finite list of multiplication rules. You may build any finite machine you like, give it 64 points, then thousands, then millions. Let every requested action rearrange those points reversibly. You are even allowed a tiny fraction of mistakes. For decades, mathematicians asked whether every infinite group could pass every such finite test if the machine were made large enough. This film is about the first concrete group, for which the answer is no. Somewhere inside its rules is one finite test and one positive error floor that no finite imitation can beat. To understand why size cannot save the model, we must rewind to the simplest reversible move. A permutation is a rearrangement that loses nothing and duplicates nothing. Every point has exactly one destination, so the move can be reversed. Here, P advances each numbered seat. Q exchanges selected pairs. Apply Q first and P second, and their two trails combine into one new permutation. We write the result as PQ of X equals P of Q of X. A group is built from this kind of composition, an identity move that changes nothing, an inverse for every move, and a rule saying that brackets do not change the result of a chain of moves. Infinite groups may contain endlessly many distinct compositions. The question is whether any finite portion of that infinite behavior can be imitated on a large finite set. A finite model is therefore a claim about local algebra, not a drawing of the entire infinite object. Approximation needs an exact way to count error. Compare these two proposed permutations input by input. 10 of the 12 inputs reach the same destination. 2 do not. The normalized Hamming distance is the number of disagreeing inputs divided by the total number of inputs. 2 over 12, or 1/6. It is not the physical distance between the output seats. It is the fraction of starting points on which the two rules disagree. That distinction matters. A model may be wrong at a small set of points while still being tested against every requested multiplication relation. As the model grows, a successful approximation must drive those fractions toward zero. Errors may be rare, but all the chosen relations must become reliable together. Now watch the order of the challenge. First, the examiner selects a finite set F of group elements. Next, the examiner chooses a positive tolerance, epsilon. Only then may the builder choose a finite set Y and assign a permutation to piece EP of G to each requested element GEG. Two kinds of test are compulsory. Multiplication asks whether P of GH agrees with P of G, followed by P of H on almost every point. Separation asks whether every requested non-identity element moves almost every point. Without separation, the builder could cheat by assigning the identity permutation to everything. If the builder can succeed for every finite F and every positive epsilon, the group is Sofic. If one fixed finite F and one positive epsilon defeat every possible finite model, the group is non-Sofic. The remarkable part is that a failure about every finite set will be forced by operations on one binary tree. The examiner needs only one permanent obstruction. The builder must survive every challenge. Consider an infinite binary address, such as 0, 0, 1, 1, 0, 1, continuing forever. The operation S0 prefixes a 0. The operation S1 prefixes a 1. A matching deletion, T0 removes an opening 0. On an address beginning with 1, it returns algebraic 0. T1 behaves symmetrically. Perform a prefix and then the matching deletion, and the original address returns. Use the wrong deletion, and it vanishes. That is the relation Ti times Sj equals delta Ij. The other relation says that projecting onto the 0 branch and the 1 branch, then adding over the 2-element field, recovers the whole space. This finite tree is only a window onto the prefix cylinder relations, not the entire algebra. Yet these 4 operations generate the binary Leavitt algebra R, and its invertible elements form the group that will defeat finite approximation. An infinite address space has been encoded by 4 small moves: split, select, erase, and recombine. Erase, and place the 2 prefixing operations in a row called S and the 2 deletions in a column called T. Split one stream into its 0 and 1 branches, then reassemble it. St equals 1. Split the 2 branches separately and check their matches. Ts equals the 2 by 2 identity matrix. The precise conclusion is that R and 2 copies of R are isomorphic as right modules. It's not a claim that R and the 2 by 2 matrix ring are the same unital ring. But complete prefix codes do produce the matrix corner isomorphisms the proof needs. By repeatedly splitting leaves, the same binary mechanism can make a complete code with any finite number of cylinders, including a carefully chosen code with 9. Those 9 slots are not bookkeeping. They're the stage on which the obstruction will act. Prefix cylinders can also move reversibly. Choose two incomparable prefixes, rho and sigma. Every infinite address beginning with rho is sent to the corresponding address beginning with sigma, and vice versa. The infinite tail never changes. This cylinder swap is an honest invertible operation. In characteristic 2, it can be built from 3 elementary units, 1 plus p, then 1 plus q, then 1 plus p again, where p sends the sigma cylinder to rho, and q sends rho to sigma. These exact replacements generate Thompson's group V inside the Leavitt unit group. The tree is not decoration. Its visible branch rearrangements are the algebraic units that the contradiction will later force into an impossible, finite model. A highly structured infinite symmetry now sits inside elementary-looking operations. Now build the exact 9-leaf code. The alpha leaves are 0, 0, 0, 0, 0, 1, and 0, 1. The beta leaves are 1, 0, 0, 0, 1, 0, 0, 1, and 1, 0, 1. The NU leaves are 1, 1, 0, 0, 1, 1, 0, 1, and 1, 1, 1. Together, they partition every infinite binary address. The elementary group on all 9 leaves is G, a copy of EL9 of R inside the unit group. The elementary group gamma acts inside the alpha region. A local copy J of Thompson's Vi acts only inside the beta 1 cylinder, 1, 0, 0, 0. Gamma acts under the 0 branch. J acts under a disjoint branch. Their actions commute, and their intersection is only the identity. Their geometry makes those algebraic facts unavoidable. This separation is the hinge. Gamma supplies rigidity, while J will supply the impossible finite demand. Two prefix replacements, U and V, now tighten the trap. Read each routing table as an operation, not as a label. Both send every alpha leaf into its left child. Their remaining columns route beta and nu through complementary cylinders. Conjugating gamma by either compressor places it back inside gamma. More surprisingly, U moves the local Thompson group J from the cylinder 1000 into 0001, also inside gamma, and gamma together with U and V generates the whole group G. So a finite imitation must satisfy 3 demands at once: 2 commuting subgroup actions, 2 self-compressions, and enough routing to recover the ambient group. None of these demands is a contradiction by itself. The contradiction emerges when finite approximations are forced to organize their components. Assume for contradiction that G has increasingly accurate finite permutation models. Draw one colored edge from every point to its image under each generator. This produces a finite labeled graph. The subgroup gamma has property T, supplied here by the theorem of Ershov and Jakin-Zaparain for elementary groups over finitely generated rings. A theorem of Gabor-Kahn says that after changing only a vanishing fraction of generator edges, the gamma graph breaks into genuine expanding components. Expansion means that every set containing at most half an island has many generator edges crossing its boundary. Apply the theorem separately to the gamma generators and to the ambient G generators. We obtain 2 partitions of the same points, many cyan gamma islands and larger indigo archipelagos. They need not agree, and there may be more and more islands as the model grows. The finite model has not become one expander. It has become an archipelago of them. This is the proof's dangerous point. Transport a gamma island through the approximate permutation representing U. Most of it lands inside some original gamma island because expansion makes a large spill expensive. But several transported islands might still select the same target. Their sizes may differ wildly, and the independent ambient partition cuts across both families. We cannot say, choose one expander component. There is no privileged component, and choosing one too early may preserve one equation while destroying another. The proof must first show that component mass cannot drift freely, then match actual components inside the same finite model. Give each point z the size m of z, the number of points in its original gamma component. Inside one ambient component, A choose the median of those vertex index sizes, m's a as a. Now compress every positive size into the bounded value f of z equals m of z divided by m of z plus ma. The median becomes 1/2. Small components lie below it. Large components lie above it. The compressor inclusions make f almost non-decreasing along every positive ambient generator. But each generator is a permutation. Across the entire finite set, total rise must equal total fall. So almost no decrease means almost no increase. Sweep a horizontal level through the values. If a substantial low region and high region remained, expansion would force too many edges across the level sets. The Corollary identity counts precisely those crossings. Therefore, F concentrates near 1/2. Within each ambient component, the original gamma components that meet at good points must have sizes whose ratio tends to 1. Expansion has converted a one-sided compression inequality into two-sided size control. Globally, the islands may differ, but the relevant local masses can no longer drift apart. Size control turns overlap into matching. A good transported component lies almost entirely inside one original component. Because their sizes are now nearly equal, that overlap occupies more than half of the target. Two disjoint transported components cannot both occupy a strict majority of the same original component. So the assignment is injective. Good transported islands match distinct original islands. On the matched intersections, fixed words in gamma preserve the transported partition. Conjugate that preservation through U, and generators of J now almost preserve the original gamma components. Notice what has happened. The proof did not select a convenient island. It first made the two incompatible partitions comparable, then recovered actual one-to-one component identities from their shared points. We still need one component on which every required finite test works at once. For a word radius L, collect all bad points: failed equality tests, failed distinctness tests, multiplication errors, edited edges, generator exits, and paths that cross a component boundary. For each fixed radius, their total proportion tends to 0. Let the radius grow slowly enough that the combined error still vanishes. Average that error over all original components, weighted by their sizes. At least one component Qn carries no more than the average. The same component therefore supports every tested gamma and J word at that stage. Its size must grow, because an increasingly large ball of distinct gamma words injects into it. Restrict the near actions to Qn and complete the missing arrows to honest permutations. One island now carries all the finite tests simultaneously. Restriction creates one final technical wound. The selected graph satisfies an expansion inequality with a small additive error, but that error can overwhelm a tiny set. So choose a largest small region whose boundary is still too sparse, and remove it. The additive inequality proves that this bad cut occupies a vanishing fraction of the component. Maximality then forces the remaining set Z to be a true uniform expander. Restrict the partial permutations again, and complete their missing values. Only a vanishing fraction changes, so every fixed multiplication, separation, and commutation test survives. This second repair is essential. A restricted expander does not automatically remain an expander. The repaired object is exactly what the Kuhn-Thompson centralizer theorem needs. A Sofic approximation of gamma times J, whose gamma graph is one uniform expander. That theorem would force J to be LEF, locally embeddable into finite groups. LEF is stronger than the approximation we began with. A selected finite multiplication fragment must embed injectively into a finite group, with every tested product exact. But J is a copy of Thompson's group, V. V is infinite, simple, and finitely presented. Every finitely presented LF group is residually finite. An infinite simple group cannot be residually finite. Any map to a finite group has a normal kernel, and simplicity leaves only a trivial map or an impossible injection of an infinite group into a finite one. Therefore, V is not LF. Contradiction. So the nine-prefix elementary group G is not Sofic, and G is a subgroup of the full unit group of the binary Leavitt algebra. Because every subgroup of a Sofic group would itself be Sofic, the unit group cannot be Sofic. That is the concrete theorem. Separately, the finite obstruction can be written into a finite presentation, producing an infinite, finitely presented non-Sofic group. The lean development formally verifies the explicit non-Sofic subgroup and that existence corollary. The full unit group conclusion is the manuscript's immediate subgroup step. The finite model was never merely too small. Local algebra demanded compression, expansion forced component sizes to align, and the hidden Thompson group demanded exact finite behavior it cannot possess. Finite permutation models are not universal.